Okay, so welcome to today's lecture on neural networks and deep learning. The plan for today is that we'll finish some last examples about knowledge distillation. So, I mean, the core we discussed on Tuesday, but there's some extensions, both like relations to other things and yeah, some related things, and then some applications to more new large language models. And then the main part of today should then be on a different way of making our models smaller, which is very successfully recently and used in most state-of-the-art large models, and that will be about quantization. So the idea is that we're no longer representing all our weights of the model and also the activations maybe in their full precision, but we do quantization, as you might have learned before, and thereby be able to make the models significantly smaller, and they're like fit larger models on fewer GPUs, and then use big models, although we have limited hardware. And yeah, that will be then hopefully the main part for today. But yeah, let's start with knowledge distillation. I hope you still remember a bit from last time what the idea was, is that we take one large model and use it then to teach a smaller model how to do that, and hopefully get better performance on the smaller model. One interesting aspect which we want to cover next is that this is related also to data augmentation and synthetic data. And that we already covered a bit, if you remember, at the end of last lecture, when we talked about sequence-based models. Because if you still can remember, we had this sequence level knowledge distillation where we mainly had our teacher network generating sequences and using then this knowledge to train. And if you see it, you can see that as knowledge distillation. But of course, you can view that also more as a data augmentation strategy, because what you're mainly doing, you take your input data, you're generating labels by your teacher network, and then you have artificial training data, which is your input data and the labels from the target network. And then you're training your network with this labeled data. So in this way, the knowledge is transferred no longer by probabilities or activations between the networks, but it's transported by the labels of the system. So yes, in an additional way, which is especially interesting for scenarios where you have now models working in different relations or having different abilities. And one very famous example for that is the so-called back translation approach, which was initially used for machine translation, but can be used for a lot of scenarios where you're generating out of one sequence in another sequence, and then you can maybe do also the reverse thing where you take your output and predict your input. Where for machine translation, that's of course very natural. You can translate from language A to language B, but you can also translate from language B to language A. It's also sometimes used in dialogue, even for like speech recognition. You can take audio and transcribe it. You can also take text and try to generate the audio. So what is the idea in back translation? So you want to generate labeled data from unlabeled, and you can do that with your initial system. So in machine translation, you want maybe to like you have your input data in one language and the output data in another. One problem if you do this, even if it's a teacher network, it's of course good, should have a good quality, but it still might not be perfect. That's why you see here a bit blurry. So you have to be sure or check how much you can trust really these labels. Did you generate good labels? Or is your model maybe not good enough and not generating the best label? Therefore, there's this idea of back translation, where the idea is if we need data from build a system which translates from German to English, it might be better not to like have a teacher which does the same direction, but we can use a teacher which is in the inverse direction. The idea is if your input is not perfect, that's normally not as bad because, I mean, hopefully in reality, you don't get bad input, you get normal input. But your labels, your output should be nice because that's what your system generated. So this scenario, the standard one might be bad because when you're training then on the new data, you're learning maybe errors that your teacher model has done. So in the back translation-based approach, the idea is, okay, our initial model for our teacher model for generating the data is not in the same direction, but it takes the labels and generates the inputs. So in machine translation, it takes the English data and generates the German data. Now what you have if you train your model, your student model, is that you have, not perfect German data, because that's generated by a teacher model, but the output, this is very good data, because that is human data that you generated. If there are some structural mistakes in the input, the system might be not as good in understanding real sentences and might be a bit like biased towards understanding wrong sentences, but your input normally will be fine, so it shouldn't be that bad. But you will always generate output which is correct or which has been at least seen. So you're not learning now if the model has the teacher model has some strange effect that it's like always putting 2 dots at the end, or I don't know, everything is lowercase. Then in the first case, you would also train it to always do everything in lowercase. But here, you only understand only lowercase, but you can generate correct input. And as normal, I mean, this type of teacher-student relation, the nice thing is here, it's not that you have a strong teacher which teaches and a small teacher which is learning from it, but what you have is like 2 components which have different like directions, and of course you can iterate now. So you can take the one translation system to generate translations, then use the other one to train on these generated translation, and then by the new system, which is hopefully better, generate more translations, and again train the first system. And so you can iteratively improve. Typically, this does not go forever. Yeah, very fast, you normally reach some type of limit where you're not really getting better. So this is then somehow, the best in some way that you can get. Any more questions on this type of data augmentation? Good. Then going in a similar direction, there's also other ways. I mean, you can try to train yourself. That is what is referred to as born again networks. So here is no longer that you really generate data. So it can be all the distillation networks that we have. So it can be response-based knowledge distillation or feature-based or so on. You can use any of these techniques. And the nice thing is that you have here 2 networks which are always exactly the same. So you can use all the things we had before on relatedness and so on. You don't have to care because the hidden representations are the same. The idea is you train your first network that is here, and then you train a similar network, the student 1, or the same network, and that gets taught by your initial model. And then you do so on, which of course the hope is that each network gets a bit better because it's also learning from what it has been before. What you then also can do is like ensemble all of these models in order to then get like somehow even a better prediction, because we know that normally if we combine several models, we can even have a better performance than just by the individual models. A similar idea is you cannot do that only one after the other. There is what is called the deep mutual learning, where you may train 2 networks in parallel and then try to keep them somehow similar. And at least for some approaches, this was then also beneficial. Of course, you have to be careful. I mean, a bit like it should be more efficient than training both of them after each other or training one for double the time. the nice thing is you might at the end take one, so it's not like an inference as big as like one as two jointly models, because you only use one. If you really use both, then of course you have to think whether this is really more efficient than training a double as large model in the end. Any more questions? See, today it's too hot. Sorry for the weather. One last outlook a bit. I mean, next week we'll also have more details on foundation models, but I mean, the general, yeah.
Could it also be beneficial to maximize divergence, to have the most dissimilar representation? Somehow one's way better than the other.
And it's more that, I mean, there is maybe work where you try to learn dissimilar things, or that you, for example, try to learn something. I mean, in language, you learn things which are language independent or so that you remove the language information from it. But making things dissimilar is always a lot more difficult. Can make easily things more similar, you just have to put them together. But if you want to put them away from each other, in which direction? So it's not as good signal. So that's maybe a bit the difficult thing. Of course, in some way, it would be nice if you try to make them most dissimilar, especially if you have, in the end, the idea to assemble them in bed. Again, you would have the ability that they are concentrating on different things and therefore might be better. So it could be possible, but I think it's not working directly. So you have to a bit think about it. This we had already, so this is a bit like the general idea of a large language model. So typically this is currently a transformer architecture where you just do next word prediction, and then you can do this type of tasks by phrasing that as a question or as an instruction which you follow up. So when you have a question, where is Karlsruhe, you put it there, you put it into your transformer without doing autoregressive decoding. You force it to read the sequence, and then you can do this autoregressive part where you predict the next word and put it in again, and thereby do that. So this is a way of large language models are there to follow or complete any initial prompt. This prompting where you put something in the beginning, and then it should somehow fulfill that. So there are big large language models which are good in doing completion tasks. And of course, there we have similar problems. So we have the issue that we have very large models, and if we want to be good and have them applied, we often also need to do some type of knowledge distillation in order to distill this knowledge into maybe smaller models. It's especially maybe even more challenging than that. At least for in the beginning, the commercial models were typically significantly stronger than the open source models that we have. And I mean, by now there's really very strong open source models, but I mean, with a big advance of ChatGPT, and so the first ones were the commercial. And here, of course, we don't have access to the hidden activation. So the only thing you have is this ability to get the output. So that's why a lot of work in the field of knowledge distillation for language model is exactly looking at the aspects we have before the data augmentation. So you have a strong language model which generates you some type of data, and then you train on this data to get a small model or a decent small model which has specific abilities and is good in this. So the scenario in one way was expressed like that. So typically a lot of works start with a closed source model which have a very strong performance, and then there's different ways of doing knowledge distillation. You can try to get examples from the closed source model and use it to train your open source model. You can also generate data yourself. So this is more the self-improvement way, where you generate more data by the own model, and then it improves. Of course, you have a bit this challenge that we also had in the back translation case, or what we addressed by the back translation case, that in self-improvement, one big issue is always you shouldn't self-improve your errors. So you should somehow find out where you're bad and not like make your errors even stronger. That is especially challenging since typically these neural networks are overconfident, so it's not so easy to detect whether they're right or wrong. And then you can do similar to what we had before. You can take some model and compress it into like a smaller type of model. How this is done is, yeah, in very different ways. As I said, normally you have this thing that you have some seed knowledge, some prompts, some data set, then you use your large language model to generate examples from that. So you have raw data, you label it. So that's a very easy case. So you really, like, you do the labeling, what is to generate translation data or named entity data we have, and then you have your generated knowledge. Typically, this one is only string. So that's a different to most of the techniques we learned until now, where we had like tried to teach by hidden activations and things like that. And then you can train your student model with these new generated data. That can be done by supervised fine-tuning, that is the standard one, by reinforcement learning or things like that, or rank optimization. The standard case is that, or the easiest case is to just fine-tune on this type of data to like then try to do the same thing as the language model does. But here it's mainly the data augmentation scenario. So you're then again have a bit the problem that you only get the one signal. So you only get this as a correct token, but you not get the full probability distribution, since you often do not have access to that in order to really get all the feedback. Good. This is most we have for knowledge distillation. Before we are now going to the next topic of quantization, are there any open questions? And then I need 1 second. Yes, sorry. Okay, so with this, yeah, we're going then for the next thing for looking into how can we quantize models. So mainly take the same models, but somehow compress them, make them into a smaller. The motivation is, of course, exactly the same thing. So we have again this target that the models get larger and larger and larger. So we have to somehow deal with how can we make these large models efficient in using less resources, especially if we want to apply them on things like smaller units, like on phones or on drones. I don't know who of you has seen some of these demo where people put language models on a phone and you can have a local running assistant. Anybody has seen? Okay, so yeah, there is models like Llama or like Fire, so which you can people put a lot of effort in running them on your phone. And typically the one important case is what we're talking about today, is making things or quantizing them. So what is why is this important? So one big bottleneck when you think about these models is the huge memory they need. Why do they need such big memory? Because they are like really huge models. So here's 3 examples. We have the T5, which is an encoder-decoder model, which you hopefully can remember this architecture from last time, which has around like 11 billion parameters. And then there is this Llama, which is one of the most famous open source models where there's different variants. And here's like one with 33 and 64 billion parameters. If you're using these models and you want to decode any sentence, these parameters, these 11 billion parameters, they will need around between 22 gigabytes or 130 gigabytes of memory just to be run. So you need to store these, like all your weights somewhere. And if you want to do it efficient, you typically want to have them in GPUs. So, however, currently there is rarely GPUs where you can store 130 gigabyte. I think they don't exist at the moment, otherwise they would be expensive. So what would you do if you're not thinking about quantization? We once had a bit of technique of what we still could do. Does anybody remember? Yes?
Having some layers, so split the model to several GPUs and having some layers on one and then just over the amount of GPUs we need.
Yes, that would what we do. Of course, it comes a bit of a cost. There isn't any, it's not super cool because you have to pay for 4 GPUs now to run the model and not one single. So the nice thing what we want to look into today is like this. How can we make these models smaller so that they fit on a single GPU? And this is for inference. For fine-tuning, the thing is even more worse. If you see, if you want to fine-tune the model, you need even a lot more memory. Does anybody know why do we need more memory in fine-tuning? Anybody remembering? So if you have your model, you can do the forward parse, that's the inference, that's a prediction. It's now independent whether it's a language model or any other neural network. Why do you need more memory when you know fine-tuning is here? So it's like if you train it, continue train it. So why do you think you need more memory in fine-tuning than just in inference? Yes?
Because our batch size is way larger, possibly.
Independent even of the batch size. I mean, inference, you're right. So you not always can have a large batch size, but sometimes, I mean, just imagine you have a lot of data you need to label or inference, and you still can have large batch sizes.
Yeah, the backwards pass. Need to be stored, the gradients.
The gradients have to be stored. That's exactly, so that's one part. There's even a bit more. So gradients is right. So that's at least doubling it normally, but this is even more than doubling because you have to store the gradient and the original one. Anybody knows anything else what we have to store? It's the correct direction. Yeah.
The computational graph for the network, right?
With
The
the,
computational graph for the backwards pass.
yeah, but normally that can be even done very efficient. But what do you do after the backward pass? You use the optimizer. We had some like Adam or so. If you use your optimizer, you have to store, we stored additional things. If you remember optimizer, you have to store the momentum and the second momentum and so on. So you have to store additional parameters for each weight. And that, of course, all has to be stored. And that makes it that we have really a huge factor here, where you need more. And again, I have to be honest, this is not purely quantization. So what is typically done, at least in these language models, is that you do quantization and then you fine tune not all parameters, but you do at the like low range adapters. Anybody remembering what that was? So we had that instead of fine tuning the whole model, you have like connections in there which approximate and which have a smaller dimension. You only train the small part because you maybe need less data to do that, and you need less memory, and you only train these small new parameters and not everything. And that of course is partly the solution here, but the other is that you do quantization and don't store the big original model. So what is stored in memory? So why is it so high? I mean, we discussed that a bit. It's like you have to store all these numbers. So all the weights, all the activations has to be stored in there, especially the weights have to be stored forever. And last time, if we have to reduce one, the first idea is if we don't have enough space, okay, can we do with less numbers? So there was knowledge distillation. Can we build smaller models to make that more efficient? The other idea is if we don't want to make the model smaller, is oh, can we have a more efficient encoding of the numbers? Can we like maybe store them not exactly, but more, but roughly, so that the memory you need for each of your parameters is less? And that is the main idea that we now have in quantization, so that you're not storing all the numbers, but that you can do a more efficient way of doing this type of calculation, or like storing the memory in there. We'll see in some ways you can even do the full calculation then in quantized space. Typically, it's really only for storing them, and you like remap them back and forth between to the original weights. Before we are looking how we can more efficiently encode our weights of the model, it might make sense. I think you all have done something about number representation in computer hardware, but let's do a bit of like 3 slides or so repetition of how we are storing numbers. There's different numbers that we can store. There's of course integers. Typically it can be stored in 3 ways. So you all know that they're stored like as a binary number. So this is like this here is multiplied by 1, this by 2, by 4, and so on. And then if you have this binary number, that is the value that you get. So that's an unsigned integer. It's like an n-bit integer, and this can have the range between 0 and 2 to the power of n minus 1. And then often we're not having only positive numbers, but also negative numbers. The easiest thing is we have 1 bit at the beginning. So you have a bit at the beginning saying whether this is a positive value or a negative value, and then all the others. There's one challenge with this one, is you have now 2 representations of the 0, because you have the 0, plus 0, and minus 0. So if you have all the others here behind 0, it's 0, and then you have like a plus 0 and a minus 0. And that, of course, might make things a bit more complicated to calculate. But typically, things are stored in the 2 complement representation, where it's a bit like the first, but the sign of the first one is minus 2 to the power of 7, which means that you then have all numbers between minus 2 to the power of n minus 1. That's 1, 0, 0, 0, 0, 0, 0, 0, and 2n minus 1 minus 1. That's 1, 0, 0, 0, 0, 0. No, 1, 1, 1, 1, 1, 1, 1, sorry, except for the first one. And which has a nice thing. Now we only have 1, 0. Everything is 0. Of course, it makes things a bit tricky sometimes, because the number of negative values that you represent is 1 higher than the number of positive values. However, especially when we are talking about neural networks, we're often not only working with integers, but we're also having like floating point numbers. So there's 2 ways, more 2 commonly used ways of doing floating point or like fractions. The one is the fixed point numbers. That means you have, again, like here in front, your sign bit, then you have your integer, and then you have your fraction, and there's, in your definition, there's fixed in where the split is. Meaning that the last one of the integer is 2 to the power of 0, and afterwards you have 2 to the power of minus 1, minus 2, minus 3, and so on. And with this one, then you can also represent numbers, real number, or like numbers with points in there. And yes, however, this is not how it's mostly done. Mostly it's done with the so-called floating point numbers, where you have the advantage that it's a bit better in representing for large numbers, you have a wider difference between the numbers, where for small numbers you can be more precise. And then what you're doing is you have the sign bit here in front, then you have 1 plus the fraction, which is the fraction bit is here represented, And then you have times 2 to the power of the exponent, which is represented here. And the exponent can both be positive or negative. You have the bias here. So half the exponents are positive and half the exponents are negative. So if you want to represent 0.265625, that's, for example, 1.0625 times 2 to the power of -2. And then you can do, this is the 1 plus 0.0625. So you, in your fraction part here, you're representing 0.026, which is 1/16. So you see that here is a 1 and everything else is 0. While here you have to represent -2, since your bias is 127, you have to represent 125, and this should be then 125. And so, which means you can like represent now floating point numbers in typically here 32 bits. So we have like, we need 32 bits in order to represent that. How exactly the separation is, there is different ways of doing that. There's single precision, half precision. There is like for NVIDIA, like you see extra ones. The main difference is like how many bits you have in total, and then how many are used for the exponent and how many are used for the fraction, meaning the exponent is mainly there for how big your range is, so how big the numbers are that you can represent, and the fraction is like how detailed you can represent the different the different numbers that you have. Okay, so this was the first short brief recap on like how numbers are represented by default, and motivated by that we can want now to see if we can do that more efficient. Is a bit wrong term, because we will see, of course, if we are trying to use less memory to represent them, we'll introduce additional errors. The hope is that the error is like not too big, and we can still get a decent, good quality. But before we are looking into that, any more questions to numbers representation? Good. So what is now the idea of quantization? The idea is that we have either a continuous signal. Now, hopefully you will all tell us, but weights aren't continuous because we have them already digital. We just learned how they're represented. So even our input weights that we have currently are not really continuous, but that's a quite large set. So the number of possible values that you can represent with a FP16 or so number is quite high, and therefore you can see that as a large set. The idea is maybe we can do a smaller discrete set and like bucket them into. So the main idea we might want to bucket. That's also done in a lot of other things. So here you have, for example, audio signal or any other continuous signal, and you can try to discretize that by saying, okay, you're doing discretization on the time, but then you do quantization here on the signal strength. You see that you're not exactly taking the value at each of the timestamps, but you're either taking this value, or this. So you have only 2 positive, 0, and 2 negative values, and that's how you're storing. And then you directly see here in red, this is of course not perfect. You have sometimes an error which you introduce, but the hope is that, yeah, since if you store the error, it's not too big, and therefore you have so more effective. So the idea in quantization is always, yeah, you're introducing an error, but the information that you're losing might not be very important for your final output. Similar in images, of course, you can do that also. You can have a more coarse-grained by pixels. You have less pixels, and you do a type of quantization, and you can have less colors representing them. So you're not taking all possible values there of RGB, but you're taking a limited set. That's now, yeah, a bit further away. So what to be more free, what does it mean if we want to do it for machine learning? That in machine learning, that typically means we try to somehow bucket our numbers. So if we have here our numbers, the weights that occur, then different weights might occur different often or so. And what we're now doing is we're no longer storing exactly the values that we have, but instead we are storing the index of this bucket here. And then we can have not all possible values, in this case between -3 and +3, but we only have maybe these 16 values or so. And you're only storing, and all the numbers from here to here, they will be all stored exactly with the same value. So you cannot distinguish them anymore, which of course introduces you an error, but the hope is a bit, we have the error, but it's not too big, and maybe for the final prediction, it might not be super important. So a typical example could be something that if you have here your numbers, and we see typically when we have floating point numbers, it's 32 bits. So there we saw that, like a floating point numbers, we have the sign bit, then we have the exponent and the mantissa. And now if we are instead, for example, replaces the 32 bits by 4 bits, we have only 1/8 of the memory. 4 bits, 2 to the power 4 is 16. So instead we can only have 16 numbers. So if we want to have 2-bit numbers, mainly we only have 16 indices. What we can do now is we can slice them here, for example, in 16 equal long bins, and then not store the exact value, but we only store the bin index, which is wars, and then we have some type of linear quantization, which means that we are storing only this. And there we'll see is the main idea in quantization, that we somehow define our new data structure, which stores the numbers in hopefully a more dense way by clustering several ones into the same. The main question is now, what is a good way of defining your clusters? So how do you define your clusters? Which numbers should be put into the same? In quantization, this is mainly called that you try to define your data type. So how you store your things. So we have seen some data types before. We have the floating point numbers, integers. The question is, if you now do a smaller value, what is a good way of defining your numbers in a way that what is the target? That's maybe a good question. What is the aim when doing quantization? Saw it already in some picture at the beginning. Yes.
Reduce the size of the models.
Yes, you're right. Completely right. It's not what I wanted to ask, because typically this is somehow what you're fixed. So you say, I want to quantize with having each number in 4-bit representation or 8-bit representation. But now there might be different ways of how you quantize. So which one would you take if you're saying, if there is different methods of doing that? Very easy now, not a complex evaluation, but directly. If you even don't think about a model, if you have now, the task is you have all your numbers, you represent them in a quantized way. What could be a direct measurement on like how good or bad a quantization is? Yes?
We could use some error metric of the distance, like mean square error, how much the values vary by putting them into the bin.
Yes, exactly. So that's the quantization error even. So how big is the difference? Maybe I haven't explained that. So typically you're not only storing the index, but you want to map them. You have to have the ability also to map them back again. So you also have to store a reference value for each bin. So if you know later this was like bin 5, if you then want to do any calculation, you need to know that bin 5 in average or like somehow has the representation 3.75. What you can do is now you can quantize, you can dequantize, and then you can measure how big the error was. So what is the difference between the original value and the final? And that should be minimum. maybe it becomes a bit clearer when we are doing one example. So one idea or so is like to do k-mean space clustering, meaning you take your weights, you're calculating some of k-means, so you're taking some mean value from that, and then you find that these four values are similar, and the centroid on that, so the mean value is 4. Then you have the orange ones with 1.5, with 0 and -1. So this would be your class. So what you now have identified is we represent our by four classes, and you see this is not. If you do that by identify what are the main classes, if you do that by k-means clustering, then it's not equal distance. So it can be, this one is like centered around -1, and this is 1, 0, this is 1.5. You see the difference here is a lot bigger than there. So it's not an equal distance, but we didn't say that it has to be. It's maybe a good initial guess, but sometimes it's maybe better to have a more dense representation at some point and more wider at the other one. We saw that already at the beginning. In the floating point numbers, it's also the case that for small values, they are represented nearer to each other. We have a higher precision, and for bigger ones, a smaller one. So if you have the centroid, that means you can now easily quantize your bits. What you have to do is you take your weights, and now instead of storing the weights of your model, you only store the bits here. So you do the mapping based on the centroids. For 2.9, the nearest value is 2, so you have stored 3 here. For me, -0.98, the smallest value, the most similar value is -1, and so you store a 0 here, and so on. So then that's everywhere you can do. What is the benefit of this now? If we're looking in how much memory we need, we see that we already have quite decent improvement here. So if these are our weights, you have here 32 bits for each number. It's 16 numbers, 4 times 4. So it's like 512 bits or 64 bytes that you need to store just to store this one matrix. If we're now storing it in this way, we have, of course, to store a bit more in some way because we have to store our 4 centroids, which is 32 bits times 4, so 16 bytes. And this one is now very effective because we only have 2 bits for each one, 16 numbers, so it's 32 bits. So 4 bytes. So in total, we're storing now the table in 20 bytes instead of 64 bytes. So we have a more efficient representation in memory in the way that we need less memory to store. Although maybe you think first this is very complicated because instead of storing just one matrix, we have to store some or 2 matrices now to do that. On the other hand, of course, there is no free lunch. So if we do this, it's nice that you're more efficient, but it comes with a cost, and the cost is that you introduce an error. But you can also evaluate. So what you can now do is you can reconstruct your weights here. Because you don't know now anymore if this was 2.09 or 2 or something, you only have your centroid value. So there's now a 2. And there's a -1, and so on. So you always take the centroid value and replace it with your index. And then you can do the difference between that, and then you have up there the quantization error. And of course, this is now the aim. We need to find a value which is, or we need to find a way where we can hopefully have a minimal quantization error. Because, I mean, if this gets too big, we're doing complete different calculation, and then your model will no longer give you really good results because it's not really you're doing just a different type of calculation. One important point is if you're doing this k-means clustering, means that quantization is for storage, so you're storing all your values in quantization here. But if you want to do any calculation, of course, you have to first map them back, do the calculation in floating point, and then map again to the other thing. So you can't calculate easily directly in the quantized field because this is now non-linear and you can't easily do that. Any more questions to this? This K-means clustering. Good. Then let's have a look at another one, which is like linear quantization. Yeah, there we'll see that with this, at least partly, you can do also some type of calculation in the quantity. The idea is in this case, the difference is that we have equal size buckets. So there is no like some bigger and smaller bucket. You can achieve that by really just learning a mapping, how you can map the weights to the quantized. So if you want to map them or reconstruct them, what you do is you take your quantized weights, then you have some 0 point that is somewhere else, and then you have some scale, and that will give you the real. So you have again a 4-bit quantization here. You can then move that around because maybe you are more interested in quantizing positive values or in quantizing more negative values or so. So for that one, you have here your 0 point, and then you have your scale. So is your numbers that you want to represent, are they very small or are they very big, in order to then represent them correctly? And then here you have your reconstructed weights, and you can do exactly the same calculation and look again on how big your errors are. So here you see there is now this time you don't find you don't find like centroids and like do different sizes, but you have directly just a transformation which transforms your weights into the quantized values that you have. And to do this, there is a quite easy formula to reconstruct your float. What you do is you take your quantized values, you subtract one parameter, and then you multiply everything with this. So R is the original number in floating points you want to have. Here's your quantized integer. Then you have the set parameter that is a parameter where the 0 should be, and you have the scaling parameter. If you now have 2 parameters, what the question is, how do we find that? So if you have now a list of parameters, and you want to like represent these parameters in your float in quantized form, the question is how can you do that? And that is like quite straightforward when you look at that. So what you have to do, what you mainly want to do is, if you have your quantized values here, you want to transfer that again to the real values, to the floating point range. What you have is your quantized area. If you have 4 bits, you have the minimum value is -2 and the maximum value is 1. If you have 2 bits, sorry, if you have 3-bit, then you can do numbers between -4 and 3, so digit. And generally between -2 to the power of n-1 and 2 to the power of n-1 minus 1. So this is, does anybody remember which representation of integers this was? Yes, the 2 complement, exactly. So that you can do to represent here your initiates name. And now you have to do this transformation, which transforms this into some floating point range between your minimum value and your maximum value, and you somehow have to map to the 0. And of course, to be efficient, you might not want to take the full scale of all, I mean, you can't take all possible values. You have to have some maximum min value, but you want to also maybe have that depending on the weights you're having, because I mean, then it will be more efficient. And therefore you have here the 4 values to consider: the minimum quantization value, the minimum value of your numbers, and the maximum values of your numbers. Based on that, it's quite easy to determine S and Z. So what we can say from this picture is that the maximum value is S times the maximum quantized value minus Z, and the minimum value is S times Q min minus that. So this is just, we take the transformation, and somehow what we want to ensure is, of course, the minimum value gets mapped to the minimum value, and the maximum value gets mapped to the maximum value. If you do both of them, you can do now subtract these two things. The nice thing, if you subtract, you see that that is disappearing. Then you have R max minus R min is S times Q max minus Q min. Now we directly see that S is equals R max minus R min divided by Q max minus Q min, which is, yeah, not surprising. A bit the scaling factor should depend on the one hand on like how big this size is. If this is very small, you have to scale larger. If this is very big, then you have to scale less. And it depends on the range that you want to cover. If this is very big, you have a large scaling number, and the other way around. So in our case, for example, if we have numbers between 2.12 and minus 1.08, and we have a binary thing here, so the numbers are between minus 2 and 1, we get in, and our scaling factor is 1.07. Now we only have to do that, and we can do it just by rephrasing that here, and then we have to round and get the value minus 1. With this, we have then our way of quantizing, so we can quantize all the values or de-quantize them to this point. Any questions to this type of calculation that we're having here? Good. Yeah, what I said is that one nice thing here is that we can also do some type of calculation within this quantized values. So let's assume the most similar calculation, simple calculation you have to do is like, for example, a linear layer. So you have some weights, and you want to multiply them with your activations to get then the output. What you now can do is that you replace S by the quantized, Y by the quantized representation, the weights and your X, and then you get what you need to calculate here. You can multiply S, so it's SW times SX to get Y, then it's QW QX minus ZVX QX minus ZX QW plus ZW ZX, which is just like multiplying these ones out. You see already the biggest calculation will be this, of course. It's like multiplying the two quantized values. That's a pure integer calculation. We can now do like one trick to make things a bit more efficient. And this goes, you see, then we'll see like several times. We often do like rely on a bit of assumptions. And if we think about weights and a neural network, they often have like more a normal distribution. So you'll have that a lot of weights are around 0, and then they are like somehow going to both directions. If we have this assumption, that means that there will be equally many numbers below 0 and above 0. And then we can do the so-called symmetrized linear quantization, where we are saying that should be 0. So we want to map 0 to 0. And that makes, of course, things a bit simpler. Then it's just S times Q, and S is just the maximum absolute value divided by Q max. So then you always map 0 to 0 and the maximum value to the max. What is the disadvantage here? Why would you not always do that? Yeah, here. Yes.
Some values may be always positive or have a mean very different from 0.
Yes, so if you quantize values where the R max is like a lot larger than the R minimum here, or the other way around, now you're wasting it because now you're forcing the model to have the same space on negative and positive. So you're wasting a lot of space. So you of course want to have this one as small as possible up there, because then your quantized values are equally distributed. If you make this bigger, that means each bucket gets bigger, which means your quantization error gets bigger. So you want to have the scale up there as small as possible, because then each of your buckets that you put there, so each of the representations is smaller. If you now force it to be the same to the left and right, you will definitely increase it. If before it was something like from here to here, then you would have like 16 buckets for this thing, and now you have 16 buckets for the whole thing. So you'll have a less effective way, which might be a bit of a disadvantage. However, weights are typically centered around 0, so there is effective, and the nice thing is that then your calculation gets here a lot more effective, and you can more directly calculate your value, because that W and that W here, these two are 0, and you can ignore. So this is a way of one way of quantization, the linear, and we have the k-means where we have variable size. And we'll see that especially for very, very large models currently, there is more an idea of going to not to linear quantization, but to a variable size, because most of the calculation is anyway done in floating points, but you can have a more effective storing of the values. Why is this the case? So one problem in the linear quantization is linear. So we have the same bucket size for everything, which means it can be that we have like only one term in there and a lot of buckets in there. And maybe, I mean, it's not also only, of course, the absolute value is important. It's also important that you maybe still can disambiguate these ones and know how important they are. And that's why there is a second way, or another way, which is quite successful in quantization, and that is called the quantile quantization. The idea is that you make your buckets now in a way that in each bucket there is equal number of elements. So here you see now we have 2 elements there, 2 there, 2 there, 2 there, 2 there. So the idea is that if there's a lot of elements around there, then you have more dense, smaller buckets, while you have somewhere else you have bigger buckets. And then you can have, the idea, of course, is in the area where there's more numbers occurring, it's also more important to disambiguate them and to know the difference. So the question is, how do you calculate that? You could now start, of course, doing statistics about each of them. However, there might be a shortcut, and we're thinking about that. We mainly want to quantize our weights. Does anybody remember what we know about the weights or assume about the weights? Any idea? Yeah,
normal distribution.
Exactly. You said there's a normal distribution. So what we can do is that we take the normal distribution, take them buckets, so that the area here is always covered by each bucket is the same. So then the probability of elements in there is always the same. So you'll have small buckets, and here you have larger buckets. There's one extra thing you often do, like even a special bucket for 0. Anybody having an idea why in this one? This is now a bit more important for if you think of implementation of neural networks. Yes?
Because the 0 value means to ignore that value that gets into this weight.
Yes. It's not only ignoring. It's often also used for masking out so that you're ignoring, I mean, that way ignoring, so that you're saying if you have a longer sequence, then you want to do, you have the mask, which is like saying which ones should be ignored. And therefore, it's somehow important to have the zero really on zero. So you ensure this also by your quantization. And so what you're doing is, this is called the normal float. You first rescale your values between -1 and 1, so that you have them distributed between -1 and 1. And then you do this quantization, symmetrical for the positive and negative values. And that you're using then to store your weight. This is the data type, the normal float, which we'll see is used in one of the most commonly used frameworks currently to store large models, is the normal float 4. So you have then 4 bits, so 16 values here, and they're distributed according to the normal distribution. So small difference around 0 and larger differences out there. Good. Any more questions to this? Then we have one last way of doing that, and that is called the dynamic exponent quantization. And here the idea was to have like a very high precision for low, very small and very large number of values, and medium for that. And this happens because like in atom optimizers and so on, you often do a division, and then it's important that if you divide very large numbers to small, you get small values, or if you do a divide by a very large number, you get small numbers, so that you still have a high precision there. It's important to have this. And the idea here is you have a sign bit here. So you see it's a bit different. And then you're doing the exponent, and that you just do by counting. So it's not a binary, but it's a unary representation. So 2 zeros means 1 to the power of -2, 3 means 1 to the power of -3. And you need one indicator bit saying that, okay, now the exponent is over, and then the rest is a fraction. With this, you're ensuring the fraction can be variable, so it's not always. Sorry, it shouldn't be the. What is? So you have a variable size here for the exponent, then you say 1 bit to get the exponent over, and here is again the normal number, which you do as a fraction at the end. This is especially used, and we'll see that is typically used for training. So a network which gets trained, while for the parameters that are stored for inference, just we're seeing large models at the moment that they're typically done in as normal float. There's one challenge, an additional challenge, and that is like outliers. So we're saying we're scaling everything to be between 0 and 1. And then we're doing the quantization. What does it now mean? So if we're doing that, we're first doing the scaling. And if we have now one outlier, let's say it's like -10 here or so. So you're doing the scaling, and now all your distribution gets somehow distributed between -10 and 4. While nearly all your numbers are between -4 and 4, like only there's this one number. Which means in total, between -4 and 4, you only have here like 6 or 7 bins. So most numbers are used here. Maybe here's one number, and all the bins here in between are not used at all. So although you're storing 4-bit values, you're really only using 3 bits, which is of course again not really efficient. So what you're mainly doing here is, in order to store this one value, you need 4 bins here where nothing is stored. And that, of course, comes, and I mean, that means you have bigger errors here because if you would scale between 4 and -4, then you would have like shorter bins, smaller bins, and therefore you would have be more efficient in the way. So this is this type of way of how we're doing it in here. We first rescale, so you have to store one scaling factor, of course, saying like how much you rescale, similar to the linear scale, and then you store the values in between. Does anybody have an idea how we could prevent that or at least minimize that? Because first, is it clear that you have here introduced somehow, you're not really efficient if you use a lot of bins where there's nothing stored. Any idea how to make things more efficient? Yeah, it's a relatively simple trick in some way, but not easy to cover. And the idea is normally we're storing, for example, you can quantize the whole vector, and so you calculate the scaling vector for the whole vector, and then you have your min and max value to do the scaling. The idea is, or maybe it's better not to prevent this, not to scale the whole vector, but do it into chunks. And if we only in one chunk have the outlier, then the values in this one chunk, they are not represented as good. But the values in all the others, they are represented a lot better. So you see the outlier here seems to be, the outlier here is in the first chunk. So here it still works. But the nice thing is now only these numbers here are not really efficiently decoded. While for the others chunks we have, the numbers are nicely distributed across, and we have a good representation of all of them. So how do we do that? For example, you can take a block size of 64. That means if you now have a vector of 125, you split that into 16 blocks, and each of them gets quantized individually. So each of them, you calculate the scaling factor so that the values are between 1 and -1. I mean, that's similar to the scaling we did before with the linear quantization. As always, there's not only advantage. Does anybody see the disadvantage of this, of splitting things into these types of blocks? Yes?
Store more scaling factors.
Yes, exactly. So we have to store now 16 scaling factors and then one single scaling factor. And that is why in this type Q-LoRa types optimization, we're doing their second step. It's called double quantization. So what are we doing? So we are first doing this quantization, which means we store our weights, and then we store the quantized weights, which is 4-bit. And then we have to store our scaling factor, so the absolute maximum, which is for each 32-bit value. And that one value, so one scaling factor for every 64 parameters, which means 32 bits for 64 parameters, so 0.5 bit for each parameter. So before you stored each weight with 16-bit, now you store it with 4-bit for the quantized value plus 0.5, so 4.5 bits for everything. Now, not super surprising, it's called double quantization. So we have a new set of numbers, so we can do exactly the same thing again. So what we're doing is we're taking our absolute values and we're doing again a bit quantization. So now we are taking each of them, representing always 64 in them in a quantized way here. That makes then 0.12 bits, and we have to store the scaling factor, the scaling factor of the scaling factors. So in total, you have now 4.127 bits instead of 4.5 bits in there. And somehow it of course makes sense, your absolute values, since all these are weights, the absolute values are not widely distributed. They should be in some ways still somehow similar, and that would make sense. Of course, you introduce again additional errors because now this one will not longer be accurate, and then you propagate somehow your error in there. Any more questions? Okay. So then for the last minutes of today, let's have a bit of a look on like how we measure it and how, what is the effect. So what you can now, for example, do is you can measure how good the performance is for a model if you take its total model bits. So you can here store your model in 3, in 4, in 8, and in 16 bits. And then you can measure how good the model is. And this is done here for large language model in mean zero-shot accuracy, so that you give a task just describing in the prompt, and then it should solve that, and you look at the performance. What do the lines now mean? So how can you have many numbers? Maybe let's start with the blue line, the 3-bit. How can you even have many points here? The nice thing with this opt language model is you have not one opt language model, but there's different sizes. So there might be a 7 billion, an 8 billion, a 30 billion or so a series of models. And then you can now see, okay, if you take the one model and quantize this, you have in total 10 to the power of 9 bits, and here you have maybe more bits. What now, of course, it's important if you compare things. So, for example, the 8 and the 16, you might be, so I assume these two models are exactly the same models, but one's quantized with 8-bit, and if you now quantize it with 16 bits, the size is double as big, because the quantization is different. And here you have the model quantized, the same model quantized with 4 bits. And now you can, but if you, so in this, so these models, yeah. But you see now here, I mean, this model, of course, the 4-bit needs a lot less space than the 8. And you can see for each, if you look and if you fix your bit size, always the best precision, the best performance you get is if you take the 4-bit quantization. So typically, if you have about a trade-off, some of the best performance is get. It might be if you really want to have the best model that you get better with these ones. But if you have a fixed budget on storage, on how big your model is, the best way here is to store it using 4-bit precision, at least this family of OPT models. And yeah, you see that there is quite a decent difference. So the 4-bit is always performing quite a bit better. Any questions to that? Good. You can now, of course, do investigate the other hyperparameters, and here are some examples of that. So here we see, for example, the block size. Sorry, not super good to read. So we have the blue line, 64 block size. We have the green line, which is a block size of 124, and 256 is the yellow, 6 is the yellow one. You see, it's not always, and again, we have the total model bits here. Of course, the model bit size is not super different. The 64-bit is always a bit bigger because we have to store more scaling, but especially if we do the double quantization, it's somehow limited. But you see that the performance is typically mostly a bit better, except for when very big models, it was a bit better to do 265 models. But in general, it seems to help to have smaller sizes in order then to minimize somehow. The bigger your block size here is, somehow your quantization error will also increase because you have a bigger size of your more different types of values in there, which means your quantization error will somehow go up. More questions on that? Then you can also compare different types of representation. And here is the quantile, the floating integers, and dynamic exponent. And you see, for example, the dynamic exponent, it works very well for training, but for inference, it's not as good. And here the orange and yellow one, the quantile and the float representation, were performing somehow yeah, the best. The last one on that is if you now have 4 bits, you can take the normal float so that you have a linear scale. You can have 4-bit float. You can have the normal float when we have with the normal quantization, or you can have the green one, which is with double quantization. And you see that if you again do the performance by bits, you have the best performance if you take normal float plus double quantization in there. Good. Any more questions about this? Then we want to do one last example, and I already mentioned it a bit. So this is one typical use case where it's typically used at the moment, and it's called Q-LoRa. So LoRa is low range adapters, and maybe you remember that if you want to train a big model, instead of fine-tuning all weights, what we did in Q-LoRa, in normal LoRa, is that you add these adapters in there so that you only fine-tune the adapters and keep the other model frozen. So you have less parameters. That means you have to also store less gradients and so on, and you have less overfitting, and so typically you can do a lot faster fine-tuning. Now, the next step in Q-LoRa is in order to, and that is somehow if you need to fine-tune a large language model on any specific task, Q-LoRa is somehow the basic thing that you would most probably at the moment do. If out of the box, this typically works decently good. So what it does is, first of all, it takes what LoRa does. So you don't train the full model, but you only train the adapters. So you only train these adapters. But then in addition, you take the full model, has of course still most of the parameters. A full model is like a lot of parameters, and then you have small adapters in each layer. Now what Q-LoRa does is that it takes your adapters, it takes your baseline model and quantizes it into a 4-bit representation. So that the baseline model is only represented by a quantized, and only your low-ranked adapters are still normal floating point numbers. Of course, you only update and change your adapters, and the general model is used to calculate the gradients and so on. Then you need to do some additional tricks. I mean, for very long sentences, sometimes you run out of memory. So on the GPU, so you do dynamically paging of some of the memory onto the CPU. But the important thing is that it used, like, for the baseline model for your base model here, it used 4-bit normal float quantization with double quantization in there, and thereby you can achieve good performance with limited memory. What that means, we can have a look at one example here. So normally when you want to fine-tune the model, you have already this big size. So what you need is you need to store your weights. Let's assume it's like FP16, so 16-bit, so 2 bytes that you have to store for the weight. You have to store the same for each weight. You also have to store a gradient, which means also 2 byte. Then you have to store the optimizer state. So you have to store the momentum, the second momentum, and some more information. So in total, that is typically like additional 8 bytes, so additional 4 numbers for each, which makes in total, you have, like, for each weight, you have to store 12 bytes in your memory. If you do that, if you now fine-tune the full model, that means you have, for the 62 billion parameters, 12 bytes means 760 gigabytes of memory that you need. If you're doing that on GPUs, it means if you're looking at current data center GPUs, it means you have something like 17 GPUs that you need to use. Okay, now the first big step is to use Q-LoRa instead of that. What does it mean? We are changing nothing here. So 2 bytes are 16 bits. So each weight is stored exactly the same. But now most weights are not changed, so you don't have to store the gradients for long. And you have to once calculate them, and then you can directly delete them again. So you don't have to store the gradients of all. You only have to do it for your adapters. And for these adapters, you also have to store the weights and the optimizer state. And in total, this is something around 0.2 bit per weight, because you have a lot less weights in there than you have for your original model. So you have like, I mean, this mainly means you have 1/5 or so of the parameters here where you store them. And then of course you have to store the weights now for the adapters, which are additional weights to that. But in total now you have 16.67 bits instead of 12 bytes here. So you are going down from 760 gigabytes to 143 gigabytes to store the model, where it's nice. Now you don't need 17 GPUs, but you only need 4 GPUs to store the whole model. And now you can do the next step and also quantum. You see now most of the memory that you need here is to store the weights of your initial model. This is like, if you think about the weights, the changes here, the adapter is 1.6 bits per weight, but this is 60 bits. So this is most. So it makes sense to think about, can we do that more efficient? And that's where quantization now comes in. So you store this in a quantizer. This is what people refer to as free LoRa. And what you do is you store them now as 4-bit normal floats. We said a bit more than 4 bits, to be honest. Why? Remember? Why is this not completely correct? What have you stored in addition to the 4-bit value, quantized value? The scaling and the double quantization, but if you remember, it was 4.1 something or something. So it's like roughly. Then you have 5.6 bits roughly. So now it fits on 45 gigabytes, which is roughly one big data center GPU. So with all these tricks, you're able now to fine-tune a very large language model still on one single GPU. Which of course increases the efficiency and makes it possible for a lot more people to do that. Of course, it comes at some cost. So we are not fine-tuning everything. We are only fine-tuning the LoRa. However, and often this is even better because you somehow are less prone to overfitting because you are training a small number of parameters. And secondly, you do a quantization error. However, people have seen that the performance is still quite good. Good. With this, we are at the end of today's lecture. We talked about quantization, which is mainly about how we can bucket things into different buckets there. The numbers, how we can put them there. So important thing is the scaling. So how do we get all the numbers in there? How can we minimize the error? By scaling smaller chunks, finding a good width of the different buckets, and doing that. Most of the work is from these two references. And are there more questions? Good. Then thanks a lot for listening, and see you on Tuesday. We have an exercise then again in China. Yeah, thanks.